My name is Andrew Penner. I'm the president of the AEE Canada East chapter. Welcome to our final webinar for 2022. Today, the conversation is going to focus on advanced heat pump technologies. Today's presenter is Wael Khalef. He's at HTS. So interestingly, Wael studied biomedical engineering, and I asked him this morning, why did you do biomedical engineering, and how did you end up in buildings? And of course, the answer was quite logical. There were some aspirations of being a doctor, but then the sobering reality of 16 years of education before making money caused the engineer in him to look elsewhere. So he has been, since graduating, working with HTS. He focuses on dealing with consulting engineers, building owners, and operators, helping them identify solutions, of course. And that's Wael. So Wael, I'm going to ask you to share your screen, and I'm going to stop, and the floor is yours.
All right, thank you very much again, Andrew. So thank you everyone for tuning in to this presentation today. So basically the topic is advanced heat pump technologies, and really my goal here was to not go too much into detail about every little aspect of a heat pump, just kind of give an overview of what it is, but how we're seeing heat pump technologies being used in kind of higher performing or advanced applications in the current market. So very quickly, how I broke down in this presentation is what you can see here. Really, we just want to touch really quickly on the basics around how a heat pump works, and including the understanding of how it's going to be able to achieve such high efficiencies. Look at the operational limitations, which is a big thing for us in kind of in in Ottawa and the East Coast for lower temperatures. Quickly look at different compressor types and refrigerants that are most commonly used in our commercial market. And towards the end, I just want to categorize various types of heat pumps and kind of achieve a common naming convention or nomenclature that is used throughout this presentation in our market. I've seen a lot of people use different terms for the same heat pump, and sometimes it could lead to some confusion. So I'm going to propose kind of a way to call them that makes a lot of sense about how you can really use them. And then towards the end, touch very quickly on VRF. It is also a heat pump, but it functions a bit differently than traditional heat pumps where it circulates refrigerant instead of water. So let's start very quickly with the basics. So looking at this, one thing we should really dig deeper into is the efficiency of a heat pump. And it's really important to understand what drives the efficiency of the heat pump so we can kind of understand where we want to make the decision or what parameters we want to make this decision for. So the COP value simply defines the thermal energy output of a heat pump versus how much electricity you have to put in for a particular period of time. So if the easiest comparison is really looking at an electric resistance heater or just an electric heater, the COP, we are going to assume it to be 1 or as close to 1 as possible. So all the electrical input I input into this device is going to be translated into an electrical thermal energy. So for 1 kilowatt of electrical energy I put in, I'm going to get 1 kilowatt of thermal energy out. So now, differentiating the electric resistance heater to a heat pump, the heat pump will use both the electrical energy in and the energy stored within a thermal source. So if I look at a residential heat pump, for example, I'm going to input electricity in, but I'm also going to take advantage of the energy stored in the ambient air outside in order to provide some heating into my house. And that allows us to achieve COPs that are far greater than 1. So for the lower example, if I use a COP of 3, then every kilowatt of input I put in, I'm going to get 3 kilowatts of thermal output out. So logically, this is a really attractive technology for us to use. So now, here's where I want to start looking into the differentiators between COPs when we're looking at complicated heat pumps. So it's really, with heat pumps, it's really possible to use both the heating effect and the cooling effect if we have an application that obviously needs heating demand and a cooling demand. So a great example would be if I look at a heat pump in a rec center, where I need to heat the pool water, but I also need to keep a gym and a couple of offices and some common spaces cool in the summer. So since heat pumps just use the refrigeration cycle to move heat from one area to another, I can basically remove the heat from the gyms, the offices, the common spaces, and take that heat and dump it to heat the pool water. And that's a form of energy recovery where I can take credit for both the cooling aspect of my heat pump and the heating aspect. So if I look back to my heat pump calculation, whenever I have a demand for simultaneous heating and cooling load, basically heat recovery between the heating and cooling systems, then I can consider that my CUP is going to include both thermal energy added and thermal energy removed, divided by that electrical input over a certain period of time. So since the heat is being shared, I can really take into account the heating and the cooling effect of the system while still only running one central piece of equipment, which is really the key aspect here. So because I can do both at the same time and I'm using the same amount of kilowatt input, then my COP can increase dramatically to very, very high efficiencies. So now that we kind of have a basic understanding of like the basic heat pump slash COP functioning, there's a couple of considerations that I think are very important to understand, especially where we define the operating envelope and limits of any heat pump. And those parameters are really going to affect the efficiency and the capacity of any heat pump. Now, a heat pump, when it starts operating, it doesn't really remain static at a certain COP. That COP will change depending on how hot I want my hot water to be or how low my ambient temperature is for an air source heat pump. In the case of a water source heat pump, that could be the temperature of my source. And in the case of heat recovery or reversible heat pumps, how cold do I really want my chilled water to be and how hot do I want my hot water production to be? So those parameters start playing around with how high or how low a COP I'm going to get for a particular heat pump. So now it's probably the perfect time to bring up the concept of lift. It is for a lot of people, it's a very common concept, but I just figured we'd touch on it again just to understand the limitations of air source heat pumps and water source heat pumps, depending on how hot or how cold you want to create different temperatures for water. So the lift, in a very basic and fundamental term, is just the difference between our hot side, which is generally considered our condensing temperature, and our cold side, which is our suction temperature. If I look at the picture I've shown here, it's basically just the saturated condensing temperature, the difference with the saturated suction temperature. So that differential of pressure is called my lift, which is essentially how much work does my compressor have to do in order to take that suction temperature all the way to my condensing temperature. So if I look at an air source heat pump in heating mode, this would be the temperature slash pressure of the refrigerant, which is absorbing heat from the atmosphere or from outside, and the temperature pressure of the refrigerant, which is going to reject that heat into a hot water loop or straight into my furnace. So in order for a heat pump to work, compressor again must be able to provide that lift, and that lift can be higher than a certain heat pump can perform. So that would set the limitation for a particular heat pump is really how much lift it can achieve. So obviously, the further the lift, the harder the heat pump will work, and this results in a lower COP and overall lower capacity. So whenever we have the opportunity to reduce the lift, that could be a hot water reset or a chilled water reset. Those two sequences of operation, if possible, will allow us to obtain a higher efficiency at our heat pump, which is a very common strategy whenever we're looking at comfort cooling applications. So again, when considering air source heat pumps, there are ambient limitations. It would be amazing for us to be able to extract heat out of -20-degree air, but obviously there are some limitations from a mechanical point of view about how well a heat pump can actually perform when it's getting really, really cold outside. So here's a great graph that just kind of illustrates that. So it shows the relationship between the outside air temperature and the efficiency of a typical heat pump. So if you look at the x-axis, that's going to represent the outside air temperature, and the y-axis represents the full load COP of a heat pump. So obviously, if you look at our yellow dotted line, around 47 degrees of outside temperature, our COP is just above 5, which is amazing. But as we get colder and colder, the COP is going to start dropping off dramatically. So it's really important that we understand these factors whenever we're modeling a particular application, understanding how the ambient temperature is really going to affect our COP and ultimately the capacity that we're able to get out of our heat pump. So it's not only outside air that just has the effect on the COP. Here we have another chart on top that shows the effect of the COP versus the outlet water temperature. So as I want to increase my supply water temperature or my outlet water temperature, the CP will decrease since the compressor must work harder to produce a higher supply water temperature using the same amount of heat in the outside air. So again, same concept we talked about in the past slide, but again, just shown a bit of a different way, just by talking about how we can reset that supply hot water temperature with respect to the ambient temperature outside. And then if I look at the chart below, that's really an interesting chart because it's going to show the effect of maximum outlet temperature compared to the outside air temperature. So if I drop below 30 degrees Fahrenheit, the maximum supply water temperature I can create with a fixed compressor is going to start decreasing, where eventually I'm going to reach a point where the unit can't produce any more hot water, and the building is going to have to rely on a different source of hot water production. So obviously, if you are in a climate where you have a lot of hours below that temperature, you will hit a kind of a proverbial wall in terms of how much heat or how much dependency you can have on that particular heat pump. So this graph is somewhat typical for a heat pump running on HFC refrigerants. Now, the good thing about our industry is every year the technology is going to get better and better. So we're seeing this outside air or the minimum outside air temp start dropping lower and lower every year. And now to add another factor to that, even better, we're seeing different refrigerants that are going to allow for way lower minimum ambient temperatures or at the same time, way higher hot water temperatures. And I'm going to touch a bit on that a bit later in the presentation, just to give you an idea of where we see those refrigerants being used and what kind of applications we're seeing those machines being used, just to show how cold we can go and how hot we can go on the hot water side. So we've gone through the COP and how lift works. Let's look at the limitations. We've looked at the limitations. We just want to look at now what type of compressors we're seeing commonly in heat pumps and different refrigerants that we're going to see used in the commercial market. So again, this might be very introductory compressor kind of presentation, but it's really important for us to look at them because we are seeing a slight change in what manufacturers are using for different applications. So if we start with probably the most popular and most commonly used one is the scroll compressor. It is a positive displacement compressor, and I'm not going to get into exactly how it works, but it is very short, definition or how it works is basically two off-center scrolls that oscillate one against each other. So it is a very robust compressor. We use it very, very frequently. And then we have two different methods generally of controlling capacity, which is a VFD, so slow down the compressor, or a digital scroll where you can unload the head of the compressor to modulate for capacity. And now, currently in our Operating Engineers Act in Ontario specifically, we are very limited in how big the machine can become without having a stationary engineer. Now, my goal is not to get into the whole Operating Engineers Act, but just to understand that there's a limit about how big a certain machine can become without starting to look at Operating Engineers Act. And then we have a vapor injection compressor, which we're going to talk about in the next two slides. Reciprocating compressors, again, a positive displacement compressor, functions exactly like your car engine. And this was considered a very old school compressor, but we're seeing it come back into market for certain applications using CO2 or different refrigerants for certain applications. So again, disappeared from the market or from the commercial market for a while. We're seeing it come back more and more into the commercial market, mostly because we're trying to achieve very high lifts, which is the reason why this compressor is used. So again, screw compressor is another positive displacement compressor, great for high lift applications. We generally use VFDs or slide valves to control or to modulate the load. And again, very limited in Ontario due to the Operating Engineers Act. And then we have the only non-positive displacement compressor, which is the centrifugal one that could be mag bearing or oil centrifs. Again, very efficient. It has more limited of an operating range because it's a dynamic compressor, not a positive displacement compressor. Again, it's very efficient, and you can use VFDs or inlet valves to basically try to modulate either the lift or the capacity. And the limit in the Operating Engineers Act is very wide. So you can use very large capacities before you have to have a stationary engineer um, on staff. And this is where I touch vapor injection. So vapor injection, essentially an economizer. We call it differently depending on which compressor we're looking at. So I'll call it vapor injection when I'm using it on a scroll, but we'll just call it an economizer whenever we're using it on a centrifugal chiller. And what this allows us to do is basically allows us to get a bigger range of operation and also allows us to achieve higher efficiencies and higher temperatures when used with a particular compressor. And then we can look at two-stage compression cycle, which is two compressors in series. And it's very common in, call it industrial refrigeration, a bit less in mechanical or commercial applications. But it really allows us to achieve a very high lift. So a very high lift for me, for example, in Ontario would be trying to produce 170 degrees glycol at a minus 13 degree ambient. So we're able to achieve, again, very high lifts and still at a reasonable COP, which is, in what I call reasonable, is essentially above a COP of 1, which is your electric boiler or electric resistance heater. We're seeing more technology starting to be able to achieve sub negative 20 ambient air temperatures. Now, obviously, where you want to use those machines versus the cost to build those machines it gets kind of a bit dramatic at those lower ambient temperatures. But again, if you have a particular application, we're seeing two-stage compressors being used for commercial applications to really achieve those really cold ambient temperatures. So obviously minus 20 won't mean much for everyone on this call. I understand that it goes from here all the way to the East Coast. But for example, I'm in Ottawa, so we do get those very, very cold temperatures. So these machines can start becoming very popular. So if we look at refrigerants, so again, I could probably spend 3 hours talking about refrigerants and the new refrigerants that are coming out. I just want to talk about what's the most commonly available and the most popular ones we're seeing. So most commercial heat pumps we're seeing today still use HFC refrigerants. That could be R410A or R134A as kind of the most common ones. Air to water or water to water R410A machines generally can produce hot water up to 130 and sometimes up to 140 in some cases. And then if we switch to 134A, it generally allows us to get a bit of a boost in outlet temperature where we can produce 160, maybe 170 in some cases, which is a pretty hot and interesting water temperature. Now, changing from 410A to 134A for a particular machine generally comes with a loss of efficiency, which means I need a bit more heat pump in order to satisfy the application that needs the higher lift or the higher hot water temperature, or using a very cold ambient or a cold chilled source from the other side. Now, where we need higher lifts or colder temperatures or higher hot water temperatures, we have alternate refrigerants that are available that we're seeing kind of come up a bit more frequently in our commercial market. And I'm going to touch on those machines in the next couple of slides. Here's another interesting one that we're seeing come back very with a nice impact. This carbon dioxide. So it is an interesting refrigerant that's kind of making a lot of waves in the industry, and we're starting to look at them inside heat pumps to create hot water, or even in some applications, steam in cold environments like Ontario or Ottawa. So if I look at the illustration here I have, we can see that the lift capacity of CO2 is really, really good. I can produce 41-degree chilled water, which is generally cold enough for almost all our applications, while still maintaining a very hot temperature water. And if I want, produce steam at the same time. And the refrigerant itself is, very environmentally friendly. Obviously, it has an ODP of 0 and a GWP of 1. So again, if I compare that to R410A, for example, R410A has an ODP of 0, but a GWP value of 2,100, something like that. So again, a big improvement when I'm looking at CO2 refrigerant instead of R410A, for example. And then as kind of the last, I'm going to call it kind of a niche refrigerant, is going to be ammonia refrigerant. So here I'm just showing you a machine that basically is a natural gas absorption chiller using ammonia as a refrigerant, which is a natural refrigerant with a value of 0 GWP. And this allows us to create a sort of a boiler that instead of our boiler operating at 96, 97% efficiency for a condensing boiler, it's going to allow us to get a bit more capacity or a bit more efficiency and give us an efficiency of around 120%. And I'm going to touch on this unit a bit later or in the next module when I talk about our specialty units. So this is where we get into some interesting machines that are on the market that I don't know if most of you have seen or heard of them, but they do serve a very particular purpose. So here we have something called a natural gas-driven recip compressor air source heat pump, which essentially acts as a boiler with around 200% efficiency. And if you look at this picture here, you might be able to kind of read all the small writing, but it's essentially a gas engine. And from that gas engine, there's a flywheel that basically drives a reciprocating compressor. That reciprocating compressor is part of a refrigeration cycle, which drives a condenser coil and an evaporator coil. So this machine will take heat from the refrigeration cycle that's pulling energy out of the ambient air through its evaporator coil, but at the same time, it will recover heat off the gas engine muffler. So that's where we're able to get better temperature, a higher capacity of water, but also at a higher temperature of water. This same machine exists as a water source machine. So again, it allows us to get very high efficiencies, but it also allows us to take advantage of this gas engine that's going to give us high temperature hot water. But at the same time, as I'm driving my reciprocating compressor or my refrigeration cycle, I can produce very cold chilled water at the same time. So if I look at the whole operation, I put some natural gas or some propane in, drive an engine. That engine drives the refrigeration cycle. That refrigeration cycle can produce hot water and chilled water. So for the applications where I have a simultaneous demand for chilled water, hot water, using natural gas, driving a heat pump that way gives me a very, very interesting machine and application I can use. And this is great for some locations where you don't have the electrical infrastructure in order to power a heat pump, but you have good access for propane or natural gas. Maybe that could be a very remote area where you don't have good electrical distribution. So this machine, as a water source heat pump really is a very interesting machine. Also, if I look at different municipalities or government entities that are trying to achieve midterm, off the gas goals, if I want a specific amount of carbon emission reduction by 2030, this is a great machine because I can use the same amount of natural gas, for example, and produce higher capacities, or because of my higher capacities, reduce my usage of natural gas or propane to produce chilled water or hot water. If I'm in the same kind of realm of gas-driven compressors or heat pumps, here we have kind of more of a traditional chiller. This will use a screw compressor, and I can get it up to 400 tons. And again, this will be able to use the same logic of what I was looking at in the previous slide, produce hot water and chilled water. And in terms of the hot water production, again, I can get my production from the condenser, but also I have kind of a hot water jacket that covers the muffler of this gas engine and extracts that energy, and then I can reject it into a hot water loop. Or if I want to just reject it to a cooling tower, that works as well if I don't have any use for the hot water. So because we're dealing with a combustion engine, we're really able to achieve very high hot water temperatures. I can get up to steam temperatures around 200 Fahrenheit, 220 Fahrenheit quite easily using the muffler from this gas engine. So this could be great for applications where I want to put a chiller on, I don't want to put a chiller on emergency power because that would cause the generator to become increasingly large. I can just put, just the electrical devices on the generator, then just power the rest using natural gas or propane. So I can significantly downsize my generator for applications like this and produce chilled water and hot water. And again, here's our gas-driven absorber again, using ammonia refrigerant. So Efficiency with natural gas, we can get above the 100% because of the absorption cycle concept. I can produce hot water up to 140. Again, I'm using natural gas, and I can produce simultaneous chilled water down to 23 degrees Fahrenheit. And these machines specifically are not made for very large applications. We're looking at very small residential applications, something between 4.5 to 5 ton modules. We've seen some applications use kind of 20 of them in parallel. But again, it serves a very niche area of a market where you want to use natural gas and still produce high temperature hot water and low temperature chilled water at the same time. Here's another interesting one that we've been getting a lot of interest and a lot of marketing for. It's essentially, I call it effluent heat pumps, but it's basically a heat pump that extracts energy out of wastewater and basically rejects it into a water loop. That water loop can be domestic hot water production. It could also be a simultaneous chilled water production if I have a cooling loop somewhere that I can tie it into. This particular machine will use R513A, and very easily we can achieve a very high COP just because the wastewater we have or the effluent water we have for a particular application in general has a decent warm temperature. So if I look at an application where I have, kitchen sinks, showers, toilets, standard residential application, most of the time we're noticing that the average effluent temperature is around 70 degrees Fahrenheit. So if you go back to the original slides we looked at for COP, we can look at 70 degrees source temperature is a great temperature for achieving very high COPs if I'm trying to heat the water up to 120, 130, 140 degrees Fahrenheit. And again, we can use this for domestic hot water production, space heating, and or cooling. So again, very interesting machine, very different from your common typical commercial applications. But again, it is a specialty machine where you have to tie in a sanitary sewer system into this machine in order to extract the energy out. Then you take that sewer water, send it back to the municipal infrastructure for it to be pumped towards the a pumping station or a water treatment facility. So let's look at heat pump technologies a bit more from the commercial side of things. So here's where it gets complicated in terms of what people call a particular heat pump. So as you can see here, I kind of broke it down between air source and water source. And under these two categories, we've classified different types of heat pumps based on how many pipes they really have. So I intend to use this nomenclature shown here as consistent as possible in almost all the presentations I do, just because it allows us to make the technologies that we describe a bit easier to understand and clarifies how you can use that particular machine. Now, different manufacturers, even for us at HTS, for example, we represent various different manufacturers, might use slightly different terminology than what is shown here. But we've chosen kind of this logic here because I think it relates how the machine, it relates the name with how the machine functions, which I think is the best way to kind of look at it. That way you don't get confused about any machine you see on the market. So let's start going by air source heat pump. So again, air source heat pump, I try to extract energy from the ambient air temperature and either cool it down or heat it up depending on what I'm trying to do. So if I'm trying to heat up a system or hot water loop, I'm going to extract energy from the ambient, put it into my hot water loop, and vice versa, it essentially becomes a chiller. So if I look at two-pipe cooling only heat pump, this is more commonly known as an air-cooled chiller. So I take heat from the chilled water loop and reject this to the atmosphere. So this is what really provides my cooling effect to my chilled water loop. Now the two-pipe nomenclature comes from the fact that I only have two pipes that I'm using, my chilled water supply and my chilled water return. So if we go down to the bottom picture, we have a two-pipe heating only heat pump, basically the reverse of an air-cooled chiller. And here we extract heat from the atmosphere and inject it into our hot water loop. So big differentiator here is in my chiller, I control to my chilled water set point, and as a heat pump, I'm going to control to my hot water supply set point. Then I have a two-pipe reversible heat pump. And this heat pump is essentially fitted with a reversing valve. If most of you understand refrigeration cycles or heat pump technology, reversing valve is essentially what allows us to switch the orientation of the refrigerant going through the evaporator and the condenser. So fitted with this reversing valve is going to allow us to basically provide heating water or cooling water, but not both at the same time. The way we have it shown here is that whenever I'm in heating, I supply hot water to a particular hot water loop. And then whenever in cooling, I will divert that chilled water into my building cooling load. Sorry. So this is most commonly seen in buildings where I have a need for heating and cooling, but not both at the same time. And then if I go to the bottom picture, we have something called a four-pipe heat recovery heat pump, which has the ability to provide chilled water, hot water, or both at the same time, as shown in, this, in that schematic below. And really, the important thing to note here is that I can control both a hot water set point and a chilled water set point at the same time. One is not dependent on the other. And the way we do it is we use the outside condenser coil or the air coil to basically extract heat or reject heat depending on the unbalances in my chilled water and my hot water loop. And this type of machine is commonly seen or in buildings or applications where I have a year-long demand for both cooling and heating simultaneously. And then we have something called a four-pipe dual condenser. And this is very different than the previous four-pipe machine we saw, because in this case, we only control one loop and the other one depends on that particular loop. So um, as the four pipe dual condenser, like the name implies, it really has an option to when it comes to heat rejection. So the heat pump produces chilled water, but I can reject that heat rejection to the atmosphere like any air cooled model. Or what we do is we include a separate heat exchanger in parallel to the air cooled condenser, which allows that heat to be rejected to a building hot water loop if required. So it's great for applications where heat recovery is needed but not available all year round. A great application for this would be I have dehumidification load where I need to produce chilled water, but I also have a big reheat load. So every time I produce chilled water, I can take that cooling effect, raise that temperature using my machine, and then reject it for a reheat loop. Then you have something, and this is kind of getting really, really interesting, something called a six-pipe heat recovery chiller, which includes three loops or six sets of separate pipes. And this unit has the ability to take heat from a chilled water loop and inject it into a medium temperature hot water loop. On top of that, the unit also includes a separate integrated model that's designed to take the medium temperature water and boost it to a higher temperature. So in this case, I refer to my medium temperature as being something around 120, 130, and my high temperature boosted water, something around 170 to 175 Fahrenheit. So again, very interesting machine that can do a lot and produce kind of two different loops of air source or hot water temperature. So we've gone through kind of the air source nomenclature and types of machines that exist or technologies that exist. Now let's look at our water source heat pump. So again, same concept. So when heating, well, we're using a water source heat pump and heating, we use water glycol that circulates kind of over whatever devices we have. But our source now is no longer ambient air. We use a specific liquid. Now that can be a condenser loop that's connected to boilers or a cooling tower. That could be a process loop that has kind of a waste heat tied to it. Or most commonly, lately we're seeing is a geothermal loop. So this is where we're going to dive into your water source heat pump applications. So again, let's start with the basic here. So let's look at a four-pipe cooling only heat pump. So you might notice that this looks, essentially like a chiller. And here, the heat pump or the four-pipe cooling water source heat pump is controlling to maintain a chilled water temperature, not the condenser side. The condenser side is just a function of the flow you send to it and the cooling tower heat rejection capabilities. So if you go down below here, we have pretty much the opposite, which is a four-pipe heating only heat pump. This looks a lot like a water-cooled chiller, but you'll notice that we're controlling the temperature on the condenser side, meaning we're not controlling to maintain a specific chilled water set point. Now, a lot of you might know this machine under a different term, like a templifier, for example, which is essentially what this is. And it should be noted that there's products that exist that allow us to control either the chilled water temperature or the hot water temperature, and that's known as something we call a water side reversible heat pump. So I can use this machine for in one mode decide I want to control to my condenser loop, and different time of the day or of the month or the year, I want to control to my chilled water temperature. So a machine exists where I can decide which set point I want to control my machine to. And that's what I call a water side reversible heat pump and not a refrigerant side reversible heat pump. So let's look at the four-pipe reversible heat pumps that I was talking about. So the reversing action here is achieved by the reversing valve on the refrigeration circuit internal to the heat pump. So this system really consists of four pipes. So we have a heat injection rejection source, which can consist of, again, a combination of boiler, cooling tower, geothermal, or whatever hybrid system or design you have, which can even integrate solar heating into it. Now, the image on the top shows the reversible heat pump in heating mode. And here the heat pump is drawing heat from the source loop and injecting it into the building heating loop. So whenever we have cooling required, in this case, the reversing valve will activate, and the heat pump removes heat from the building loop and rejects it to the source loop. So typically heating and cooling is available, but they're not done at the same time or simultaneously. This is where we get into the simultaneous applications on the water source side. So we have something called a six-pipe dual condenser. And again, we make the distinction that as the name mentions it, is a dual condenser, which determines that there's two different areas where I can reject my heat as I'm controlling to my chilled water set point. So if I look at this machine, I have three distinct loops or six pipes, as we can see on this picture. So we have chilled water being produced and a choice when it comes to heat rejection. So I have a condenser heat exchanger, which is tied to a heat rejection source, like a cooling tower, for example, or it could be geothermal, similar to how a water-cooled chiller would be arranged. However, in this case, I also have another condenser, which is arranged in parallel to that first condenser, and that could be tied into a building heating loop. So whenever heating is required in my building, instead of rejecting my heat that I extracted from my building cooling loop, instead of putting it to the cooling tower, I can reject it to my building heating load. And that heating load could be reheat, could be space heating, could be domestic hot water preheat. It could be whatever application you have that has a hot water demand. So again, it's a great application or a great machine to use whenever we have a need for heat recovery, but building heating is not required year round. This is where it gets also very interesting for us, is whenever is something called a six-pipe simultaneous heat pump. And that heat pump has three distinct loops: a heating loop, a cooling loop, and a source loop. Now, those heat pumps, we generally only use them whenever we have an application where we have simultaneous heating and cooling that is required for a significant portion of the year. We're not looking for simultaneous operation for, 10 hours or 20 hours a year. We want something that has a high quantity of hours where we have a simultaneous demand, and this is where this machine starts to make sense. Large buildings like colleges, universities, labs, rec centers, stuff like that. This is where we see these machines being used. Six-pipe heat pumps or systems like this work by using multiple different modules, like we see at the bottom of the screen, and we'll have multiple heat pumps in smaller capacities, kind of arranged in parallel. And this system, how it works, it will look at the chilled water temperature and the hot water temperature and will aim to always run in heat recovery mode. So moving heat from the chilled water loop to the hot water loop. And whenever my hot water loop and my chilled water loads are not even, so I have unbalanced loads, there will be a point where I can just share that energy, which is where I'm going to start to dip into my heat rejection or injection source. Because specifically, if I look at this picture, I have two temperature probes, which means I'm controlling to my hot water loop and my chilled water loop at the same time. So at this point, when we have unbalanced flows, is where the modules will start utilizing the source loop. So for example, if I have more cooling than heating, then I will dump some of that heat from the chilled water loop into the source and vice versa. If I have more heating required than I have cooling rejection, then I'm gonna extract some of the energy from my source loop to reject it into my building heating loop. So again, it really makes sense whenever I have simultaneous load applications. But again, it can really work well with unbalanced loads since I have my heat rejection or injection source ready for this application.
Hey, Weil,
Yeah.
just a quick question here from the audience. Would the six pipe simultaneous system be applicable in like a district heating type application for campuses or other small district systems?
Yeah, smaller district systems, these machines don't exist to like 1,000 tons. They're, I think, limited closer to like 200 tons a module. So, if you have 1,000 ton, you're looking at a couple of machines. But if you have, very large district applications, a couple of, thousands of tons, you don't want to have a district plant with like, 150 of these or something like that. So yes, you can, a great application for it. Um, but if you're looking at a very large district, there might be different technologies, different applications where you can kind of configure a machine for it. But yes, you can use it.
Great, thanks.
No problem. But then this is a machine, again, same concept as what we had on the air source side, but we call this one an 8-pipe simultaneous heat pump. And it's just basically the same thing as a 6-pipe system. However, we add a separate but integrated module built in, which is designed to boost some of our median temperature hot water to a higher temperature. And again, the higher temperature can be used for whatever application you want. Since the high temp heating load is 160 to 140 or even a bit higher, we can use that to actually do domestic hot water production. Now, the heat exchanger that's built into this machine is not a dual wall heat exchanger. We're going to talk about domestic water in the next slide, but essentially you can raise that temperature high enough that you can run it through a double wall heat exchanger and then make some hot water production. And the medium temp hot water loop, chilled water loop, and a source loop will act the same way as the previous 6-pipe heat pump. But now this separate high temperature module will be essentially controlling to the high temperature loop. So this way, if we need cold chilled water, some medium temp hot water for some space heating or some radiators or stuff like that, and we have a demand for high temperature hot water, we can achieve this all with one packaged system. Let's look at domestic hot water production. Again, another very, very important or popular topic for heat pump technologies. Sorry. So if we look at using heat pump to produce domestic hot water, again, it's a very interesting method because we're comparing heat pumps to your traditional way of burning fossil fuels or using an electric resistance heating machine. Now, using these domestic hot water heat pumps, as we looked at operating limitations before, we are able to produce up to 150-degree water using a double wall heat exchanger. So that means we can fully comfortably produce 140-degree domestic hot water production. Our limitation here, again, is how cold our source side is going to be. That could be air or that could be water. And again, we can use geothermal field as when we were looking at the water source side of things to produce, to use it as a source for domestic hot water production. So I've touched on this just a bit earlier, but there are a few things to consider whenever we're going to look at domestic hot water production. And most importantly is that we need to use a double wall heat exchanger instead of a single wall. And you're going to want to ensure that these packages or these heat pumps that you're going to use are certified for use with domestic water. So we're looking at an NSF 61 certification. That's really important for you to consider whenever you're looking at these machines. And then the last thing of a very important consideration is everybody needs to understand that when we're looking at heat pumps or the heat pump concept for domestic hot water production, it is not an instantaneous domestic hot water production. It's not meant to be used that way. If it was meant to be used that way, heat pumps for domestic hot water production as an instantaneous method will be extremely expensive. Our goal here is to have a smaller recovery rate using a heat pump, but have a larger amount of storage, domestic hot water storage tanks to be used in conjunction with the heat pump. If you want to achieve, your instantaneous load like you do with an instantaneous water heater using heat pumps, there's in no way you will ever be able to achieve to find like make financial sense of that application. Using heat pumps for domestic hot water production must be coupled with domestic hot water storage tanks in order for the application of application technology wise and financial wise to be able to make sense.
Hey, well, a quick question on that.
Mhm.
Do you have a rule of thumb storage volume based on application? Like, I imagine what you'd require for a home would be different than what you'd require for an office building or a community center.
Yeah, it really depends on the analysis we do for what is the peak demand of hot water for that particular application, and also what temperature you would like to store your hot water at. Most commonly, we see 140, but we've seen some applications where they would prefer to store it at 150 or 160, and that really changes the amount of storage there is. So there's no rule of thumb really. I think it's would be prudent to just do the analysis every time. Sorry, in order to determine how much MBH I can get out of my domestic hot water, and what type of how much domestic hot water storage I want to couple with that in order to have the kind of the best solution possible for a particular application. So unfortunately, I wouldn't have a rule of thumb. I would just do the analysis every time.
Well, I kind of like that answer. I'd rather us do the analysis every time than apply a rule of thumb. But
Yeah.
thanks for making sure we all remember that.
Well, so if I look at the heat pumps available for domestic water production, um, we have an air source domestic hot water heat pump, which is interesting because it will extract heat from the ambient air and then produce domestic hot water on the other side. And where I can use that, so my primary function in this case is producing hot water, but the secondary function is because I'm cooling down that air, I can put it in an area that has some waste heat available to it. So I can put this heat pump in a mechanical room where there's boilers and other equipment that's there, and that will help to cool down the mechanical room and consequently produce hot water on the other side. You can put it very high, close to skylights, where there's a lot of stratified air at the top, and cool down kind of the higher section of your space just by extracting the energy for domestic hot water production. And then another way is just to input it into a specific dedicated space cooling application where you have a cooling demand and just use it from the air side in order to produce hot water side. In this particular machine, we can produce domestic hot water up to 150 Fahrenheit, which is excellent. And our minimum source entering air temperature is around 40 degrees Fahrenheit. So as you can see here, there's your limit in terms of lift about what that compressor can really do for an air source machine. Same concept, but a water source heat pump. Again, primary function, produce hot water. Secondary function, I could use it as source water cooling. So I can basically tie it in series with a cooling tower and basically allow my cooling tower to have less load on it by pre-cooling the water going to the cooling tower. I could connect it to my chilled water return loops. I can allow my chillers to unload while using that energy to produce domestic hot water. And same thing for geothermal. And again, same limitations in terms of domestic hot water leaving temperature and my minimum source entry temperature. Here's another one we're seeing a lot of interest in is using CO2 air source heat pump for domestic hot water production. And again, we're using transcritical refrigeration here because we're using CO2. It works great on large temperature differentials, which is ideal for domestic hot water production because your domestic water in Ottawa, for example, we always assume it's coming in at 40 degrees Fahrenheit. and I want approximately 100-degree rise. So I'll come in at 40 degrees Fahrenheit and then come out at 140, which is exactly what a CO2 heat pump will like to do. And very easy to achieve very interesting COPs. So if I look at an air source heat pump at the average hour, average coldest temperature hours in Toronto at 44, COP of 3.2 is very easy to achieve. One big thing I want to note here is that on this picture, you can note that there's an intermediate heat exchanger, since the condenser coil in this air source heat pump is not a double wall heat exchanger. And this could be bad in a way because you lose that approach on the hot water produced by the air source heat pump and how much you need on the building side. But because we're using CO2, it's very easy to achieve higher temperature, 150, 160, 170. So we can produce higher temperature hot water at in a very efficient way, and then step it down through that intermediate heat exchanger, which is going to have a double wall, and then we have our domestic hot water storage tanks on the building inside. And now, without getting into too much detail, whenever we're looking at heat pump applications for domestic hot water productions, we can really benefit from intentionally stratifying some of the storage tanks, as you can see in this image. So the tank that's closest to the hot water production will be the coldest one, and the one furthest will be the warmest one. And we have a different way of stratifying these different storage tanks, and the quantity of storage tanks will depend on how much space we have. But again, we want to create some sort of a stratified tank to basically have the hottest on one side, the coldest on the other side, so that the coldest is the temperature or the water that goes into the heat pump, thus creating the larger temperature differential, which is going to cause the heat pump to work in the most efficient manner. So again, whenever we get into heat pump applications for domestic hot water production, really we have to use um, a different approach about how we design our storage tanks. We do not design them the same way as we're going to use a gas-fired domestic hot water heater or just an electric water heater. Again, same concept, same machine exists, air source and water source. If I look at, we have here the water source, for example, very easy to produce 185 degrees Fahrenheit. And we can have on the other side, source fluid down to 14 degrees Fahrenheit. And if you look at just this graph, it's really easy to get the COP of up to 5 for a machine that's able to produce 477 MBH, which is a good amount of domestic hot water production. And again, this machine, because it's CO2, uses reciprocating compressors. So again, great for high lift. It can go down for very low temperatures or very high temperatures, depending on which side you're looking at, and still achieves that in very interesting and high efficiencies. And again, I've done this for a different presentation, but I just wanted to look at different fluid outlet temperatures for hot water and at different source temperatures. So if I'm trying to produce 140 degree Fahrenheit water and I have 45-degree temperature as my source water, I'm able to achieve a COP of 4.5. And again, if you could draw the same kind of comparison to produce 158, 176 Fahrenheit, again, very high and very interesting COPs for a application where I'm going to use CO2 as a domestic hot water heat pump. And lastly, this is kind of the last module, which is just going to touch on VRF concept in heat pumps and what we're seeing being used in different applications. I think still have a couple of minutes here. So VRF, without diving into the deep theory about VRF, it's really important to understand that it really functions almost similar to a hydronic heat pump, but instead of circulating water through the system, it's going to circulate refrigerant. Now, if I look at what different manufacturers have in the market in terms of air source heat pumps, mostly kind of draw a line between a standard air source heat pump and a cold climate air source heat pump. As you can see, the standard one will continuously operate down to minus 13 degrees Fahrenheit. And then a cold climate version of that same heat pump will be able to operate continuously down to minus 22 Fahrenheit. So for someone that doesn't necessarily need to operate down to -22, you don't have to pay the premium to go to the cold climate heat pump. But for example, for us in Ottawa, it gets really cold, so -22 is really the machine we need whenever we're trying to use it in heating. Sorry. Again, here's another same comparison in terms of temperatures and capacity. So if I look at a comparison between my cold climate machine and my standard machine, this graph is really going to demonstrate how much of its nominal capacity I'm able to maintain as the outdoor temperature starts decreasing. So if I look at this graph, I can look that the standard machine will start derating its capacity at around 25 degrees Fahrenheit. But if I use that same machine as a low climate version, I'm still going to be able to provide 100% of my nominal capacity down to 0 degrees Fahrenheit. And after that, it's going to start derating, which ends up being around 60% of its nominal heating capacity at around -22 Fahrenheit. So obviously, when we talk about very cold temperatures, it's really we get a lot of the questions. Okay, well, what happens when you reach this very low temperature? Does it just shut off? And really, inside this air source heat pump, there's no outside air temperature switch, so it doesn't measure. Oh, I'm at -22. I'm going to shut off. Essentially, what it does, it's the process of logic within the machine is going to say, I'm going to monitor my refrigerant pressures. When it gets too cold, I'm going to start unloading the capacity, and then at some point it will cut on low suction pressure. That being said, whatever is published data, it's guaranteed to be operating down to those temperatures and give you the published um, corresponding capacity for heating whenever you're using it in a heating application. So the other logical question to that is, what about backup or auxiliary heating? So we have obviously many of our office buildings or comfort cooling and heating applications generally in Canada will have a high heating load demand, and will also end up with temperatures that dip below the guaranteed range. So it's really important to consider if my ambient temperature will drop below the temperatures that are safely published in a manufacturer's catalog. We really need to understand how we can tie in auxiliary heating. That could be baseboard heaters, at the perimeter, in-floor radiant, or it could be, electric heating coils and the ducts kind of in series with the fan coil that's connected to the VRF system. Again, just methods to ensure that if you go colder than, if you're sizing your heat pump for 100% at 0 degrees Fahrenheit or 60% at -20 degrees Fahrenheit, if at some time you dip below that temperature and need more heating, you really need to look into a certain method of backup or redundancy to your heating system in case something happens. In Toronto, in the GTA, we have many projects where we don't have any backup heating just because Toronto has warmer, cold temperatures. But in Ottawa, for example, we do dip, below the -20 and definitely below 0 Fahrenheit, which creates a lot of hours where we might not necessarily have our nominal heating load, and we might have some units that will trip on low suction temperature. So what we've done in Ottawa is we've bought one of our low ambient, low climate or low ambient heat pumps, and we installed it on the roof of our building, and we installed a fan coil inside our warehouse, and we're doing testing right now to see what temperature in Ottawa we're going to measure in the winter, and if the unit, how much capacity will the unit provide down to -22 or below, and at what temperature will the actual unit trip. Uh, and this is kind of testing we're going through this winter. So we'll have some good data, some interesting information to share with whoever is interested about how this air source heat pump will behave in a very cold environment for heating. Again, same concept, VRF, but we can use it on water source. And here, the standard versus low climate isn't as drastic. Standard will be whenever you're using it with a condenser loop, and geothermal or low climate in this case, or low temp climate would be whenever you're using with a geothermal application. In Ottawa, again, our geothermal fields will get down to the 30 to 25 degrees Fahrenheit. So we do need that extra lift on the geothermal heat pump or geothermal water source heat pump for the VRF in order to achieve that higher lift required. What changes really between both heat pumps? It's very similar. Some items are changed and some accessories are added, like added insulation, because the water entering the heat pump will come back really cold. So we want to avoid, ambient air to condense on the evaporator um, heat exchanger inside the heat pump. And something that is a bit particular whenever we're using water source VRF is something called this two-stage heat recovery. So what we can do is we can recover heat from different zones, areas, or indoor fan coils and share it with each other. So if I look at the second floor here, I can have one unit in heating and then the other three in cooling. And whatever heat rejection I have, or whatever heat I'm extracting out of the spaces on my cooling heads, I can basically send it to my indoor fan coil that needs heating. So that could be, partial heating. If I look a bit below, kind of a full heat recovery. So whatever my two indoor fan coils need cooling, the other two need heating, then my water source unit is basically almost doing no work, is just helping circulate the energy between one space to the other. Now, on top of that, if I look on the right-hand side of the slide, I can tie all these water source machines into a common condenser loop. So that means that if I have a space that's fully in cooling or fully in heating, that energy gets rejected to the same common condenser loop, which means that I can share that energy with all the other units that are tied together by that particular loop. So a great example would be if one side of the building might require cooling, which could be kind of a data center application or some electrical room, but the other side is perimeter offices with a lot of fenestration. You can basically take that heat rejection that's being provided by the data center electrical room, dump it into your condenser loop. That condenser loop raises in temperature, goes circulates all the way to your indoor to the water cooled unit that's serving this office space, extract the heat, and basically share energy that way. So again, very easy to achieve that whenever you have a common condenser loop. Again, we've seen this concept many times now during this presentation, but again, really important to draw the relationship between COP of the equipment with respect to the inlet water source temperature. So anytime you're able to raise that inlet water temperature, you're going to get a good bump in COP, a good bump in efficiency, and essentially in capacity. So the higher you're able to maintain the inlet water temperature, the more output you're able to get out of your equipment, and also better efficiencies you're able to get. And then finally, kind of the last concept before we end this presentation is really how to use heat pumps in ventilation, especially when we're talking about VRF applications. So this is really interesting because we're seeing ways to integrate heat pump technologies and air handling units and ERVs. So before, if I was using a DX system or refrigeration system, I would only be able to use it for cooling. I would put a condensing unit outside, I could put a DX coil inside my air handler, and this machine would be only able to provide cooling. But now with the development of VRF technologies, we can use the same coil for heating as well, and I can use my condensing unit that could be air source or water source to basically extract or reject energy to my DX coil that's going to be inside my air handler. So if I look at it here, I have my heating side of things. Draw air straight from outside through either a preheat coil or a energy recovery device, and then I can run it through my DX coil that's connected to my air source condensing unit. And then in summer, I can use the same thing here, where I get in very, very warm, run it through an energy recovery device, cool it down, and then run it through that same cooling coil that's connected to my condensing unit. And again, I only have it shown here as an air source heat pump or air condensing unit, but you can swap that out for a water cooled condensing unit like we've seen in the previous couple of slides. So very interesting application now where we can, instead of just using a standard VRF fan coils, we can tie it into an actual air handling unit coil or a custom, air handling unit application or ERV to basically be able to use the full potential of that heat pump technology with VRF. And I think that's about it. So I think we're almost right on time. Andrew, I think we're 10 after. Thank you very much for tuning in and listening. And please, if you have any questions, I'd be more than happy to stay on the line to answer.
That's fantastic. Well, thanks so much. I think most of the questions we tried to answer along the way. There wasn't as
Perfect.
many, but I think that's largely because the amount of detail you provided was so good. But there was one question that I didn't get to while you had the slide up, so I'm saving it now to the end, and it's related to the Piranha system for wastewater
Yes,
um,
sir.
heat recovery. So the question was like, what are the applications for that machine? Like, is there some application kind of go tos, size of building, wastewater
So,
flow, et cetera?
so great question. So the Piranha comes in three different sizes. We call them a T5, T10, T15, and it could drop as low as 12 GPM. So anywhere you can tie into the sewer line, sanitary line, that could be a decoupled one or a centralized one. You can use the Piranha in there as well. Uh, and it's any application where you need domestic hot water. So the residential side of things is a great potential for this, where you have a couple of peaks during the day. In the morning, everybody's going to go take their showers, so you're seeing a significant inrush of warm temperature water going down the drain. So if you can tap into that main combined sewer for your building, you run that water through this heat pump, you cool it down, and through the refrigeration cycle, you'll be able to take that energy, decouple it, and you reuse it to preheat your domestic hot water, or not only to preheat, but to provide all the domestic hot water production you need for a particular building. So it can be very small. There's also a different version of the Piranha, which is called the Shark unit, which can be applied for district applications. So it goes up to 4,500 GPM of effluent flow that you can extract energy out of it. And just to, without getting too much into detail, because this is a presentation on its own, but inside the Piranha, like the wastewater is completely decoupled from the hot water or domestic hot water by a double wall heat exchanger on one side and a full refrigeration cycle inside. So you have wastewater, refrigerant, double wall heat exchanger. So there's no obviously no contamination or not even close to it. And it's a completely sealed and vented system. So if you have this in your mechanical room, it doesn't smell at all.
Are there any specific permitting limitations around applying one of these in our
So it
buildings?
depends. It depends on the municipality. So we have a couple installed in Ottawa, and it really depends on the inspector. Generally, the limitation here is how you deal with the wastewater storage tanks. The storage tanks are designed to basically not hold the tank, but slow down the flow of the wastewater. So, say you have an incoming flow, it goes through a big tank, but that tank also has a gravity drain coming out of it. So, basically, wastewater comes in, slows down in this tank, and then it's also leaking, not leaking, but letting the wastewater leave on the other side. And what this allows us to do is have a battery of wastewater energy sitting there, slowly moving through a pipe where we can take that energy out of it or that effluent out of it, pump it into this heat pump, extract the energy, and then as soon as we're done with that energy or that wastewater, we just send it back to the municipal side. So the limitations in terms of permitting is essentially how you perceive or how you can install the wastewater storage tank, because in some municipalities the law is that you cannot impede the flow of wastewater if you're able to avoid it. We are working on a national building building code, how do you call it, an exception, or I forgot what it's called, but basically a way to have the Canadian Building Code adopt this method um, of use of a wastewater storage tank in order to not have any issues in any municipalities. But just to mention, we have these installed all over Canada, where the inspectors basically said, okay, like I'd like for you to do it this way. We just basically added a bypass line somewhere or stuff like that, and it's been working fine.
That's awesome. Um, kind of on a similar line, but this now we're focusing a little bit more on the ops teams. Are there any O&M and training kind of concerns or sensitivities around a system like this?
So obviously, when you talk about effluent to wastewater, everybody's gonna have a negative connotation to it, thinking it's dirty and it smells. Um, so a couple of things. So you have sump pumps or wastewater pumps. Those will be the same types of wastewater sump pumps that you'll have to maintain. So you have them on a chain, you pull them up, you kind of inspect the probes and stuff like that. Um, whenever you at a regular cycle. If I look at the heat pump itself, inside this heat pump, there's a big stainless steel tank. That's a big open tank, and that's where the wastewater comes in to be. This is essentially the evaporator. So whenever you go to maintain this, and again, I need to mention that the inlet pipe going into this piranha is a 4-inch connection. So any sanitary system in your designs, a toilet, for example, it's a 3 or 4-inch system. So if anything can go and flush through the toilet, it will pass through with no issues through the piranha. Now, the only tank or the only device where the wastewater touches the piranha is this big stainless steel tank. So there's no baffles or none of that. Comes in, comes out. Whenever you have to go do maintenance, and the maintenance on the wastewater side of this piranha is just cleaning the inside of the tank. So automatically you go press a button, say, okay, I'm going to maintain this. The system will drain the tank completely and prevent it from refilling with wastewater. And all you have to do, and again, the piranha isn't a very tall unit, it's probably like 5 feet tall. You take the top off, you take the top off the stainless steel evaporator, and at that point it'll be completely empty. So all you have to do is, if you have biofilms that are forming on the outside, you basically just grab fresh water, soap, and a scrub, and it's open to the atmosphere at that point. You just clean it up and flush it down, and that's it.
Awesome.
Hey,
That's great,
Wael,
man.
I have a just a follow-up note on that, just for I think along the lines of what Andrew was asking, where it's applicable. I find, to your point, that you kind of mentioned if you can tie into the main sewer line, you can heat a building. So that's kind of what we found in our projects, that a building on its own typically does not generate enough wastewater to heat, for its own heating purposes, maybe for a small portion of the building. But if you really want to have leverage wastewater to heat an entire building, you've got to tie in to some sort of sewer main. So it's applicable to some buildings, but it's not necessarily a solution for each individual building to take on their own. It's going to be the ones that kind of tap into the sewer first, I guess. And
It,
yeah,
I would say it depends, because the variable here is how big your storage tanks can be. If I can collect enough wastewater over a certain amount of time, then I can have a battery of energy ready for me to produce domestic hot water through it for a whole building. I can also use more than one piranha in
sure.
parallel.
Domestic,
So
yeah. No, sorry, I meant
yeah,
space heating, but yeah,
gotcha. Okay, yeah, for sure,
I could see
for sure.
domestic being more realistic for sure. Yeah, that's true.
You're right. We looked at we did a study for a pumping station in London, Ontario. Obviously, pumping station was receiving around 3,000 GPM of effluent flow from different municipalities, and the goal of that pumping station was that it was completely. They wanted to heat it completely using geothermal heat pumps, and what we noticed is that just based on the heating demand of that pumping station, just us extracting 300 GPM of that effluent flow was enough heat and energy to extract to heat up the whole pumping station. So imagine you have 3,000 GPM coming in. We only have to take 300 of it, run it through a shark, not this unit, but a shark unit, extract the energy out of it, and then we're able to heat the whole building through it. So it really depends on the type of building we have. But you're right. And generally, there's not enough wastewater for you to heat up a whole building space heating wise, not domestic hot water production wise, unless you have a significant amount of effluent or you're able to use very, very large storage tanks.
Hey, wow, one more question about this. And the question is related to the distance between the unit and the sewer line. Are there limitations with proximity between sewer line, tank, and the heat pump?
At that point, it's a civil challenge. Do you want to pump it up and gravity drain it through the unit? It's only piping at that point, so you can have it as far as you want. Of course, you're going to want it to have as close as possible, less wiring between the panel of the Piranha and the wastewater pumps to tell it, start pumping wastewater back into my tank. Limitations, not really. You can have it fairly far, although I don't know why you would want to. If you're able to create some type of wet well where you can draw wastewater, put it in a well, and then you draw from that well to the Piranha, and then from that, whatever comes back from that well, you send it back to the municipal. That's probably a better application or a better approach to a system where you're very far from a very large water main or a sewer main.
Awesome, thanks. So I think that wraps up the majority of the questions, but I had one more, and it's a more broad. So we many of us have been in conversations and probably heard professionally and perhaps even outside of our professional lives about the drive for decarbonization and how the electrification of our heating systems in buildings is just one of the pathways to decarbonization. I was wondering, from your perspective as an applications engineer, if you could speak to the uptake of heat pumps in perhaps applications that would have traditionally been served by natural gas appliances.
hmm It's a great question. I think in the past, say throughout the beginning of the pandemic, where we used to see a request for an air source heat pump, like air to water air source heat pump, probably used to be, once every month. And now we get multiple requests every week. So everyone has fully decided to adopt this and start looking at it as a viable solution for their building. Luckily, in Ottawa, we do see Ottawa and Gatineau. We do see a lot of geothermal. So I think the geothermal side was already adopted significantly for water source heat pump, but we are seeing them at a larger scale, as well as the addition of a lot of air source heat pumps. The biggest change lately is using it for domestic hot water production. If you look at using a gas-fired domestic hot water heater, you can notice that there's a big capacity of gas required in order to heat domestic hot water. But if you're able to use heat pump for it, that's where it becomes really interesting to try to decarbonize a specific building. And this is where we're seeing a lot of consultants adopt and look into this technology. Especially very recently is the CO2 machines that are interesting because CO2 is so adequate for cold entering temperature and very high hot water temperature leaving the heat pump. So we are seeing a significant uptick in heat pump requests for almost any application possible.
Well, that's good to hear. It's good to hear that it's actually getting into getting into the ranks of the engineers and the design teams.
Yeah.
So
How to design them are different though. Like how do you design a domestic hot water system using heat pump instead of instantaneous electric heaters or gas-fired heaters is very different. So there is a bit of a learning curve about how do I apply it? How do I change my design philosophy to use it properly? Same thing with air source heat pumps, factoring in things like defrost operation, system volume, all these items become very different than your traditional way of just using a boiler with a pump. So there's a big learning curve in terms of properly designing the systems, but we are seeing extremely high increase in interest in heat pumps on the commercial and large capacity side.
that's great. Well, thanks a lot, Weil, for taking the time this morning. For those of you who are in the Ottawa area, you'll know that it snowed last night, and it snowed a fair bit. Weil got up super early and braved the winter conditions to get to the office, so that he was ready for this morning. So, Weil, thanks for taking the time out of your day to do this for us. And
My pleasure. Thank you.
yeah, I think it was a really great presentation, and certainly gave the folks who attended a little bit of inspiration on the very broad range of applications where heat pumps can be applied. So, thanks again for tuning in. This was our last webinar for 2022. We will come back with a full roster of webinars in 2023. So, certainly, if you've followed us on LinkedIn, watch for those there. And again, thanks, Weil, and have a happy and safe holidays to everybody who are listening.
Thank you very much.
Right. Cheers.